Remember, I said chapter 19 is done, but here's a bonus video for you which will help you to hopefully tackle some of past year questions that may appear. It hasn't appeared in a long time. But anyway, before we go into the today's idea, I have one question for you. I want you to think of something in your house where when it's dark, suddenly it will turn on by itself automatically. Can you think of something in your house where suddenly it will turn on by itself when it's become dark? Maybe in sunset or nighttime, it will turn on. We think of, oh, the light there or something, no sensor thing. And you may ask why it turned on. Oh, because got sensor lor. So what is the sensor actually? There's this very cute little component in the sensor that can detect light. And it's very clever one. You see, oh, dark already, time to turn on. We're going to look at today what we call the LDR, the light dependent resistor. So we're going to focus more on the LDR lah, because thermistor we already looked at it before in the IV curve video. Remember we talked about thermistors, when it's hot, resistance change, things like that. When it's cold, it's different. So after this end of this video, hopefully you'll be able to explain what's a LDR, what does it even stand for? And you need to know especially the resistance, and L here is light intensity curves of LDR and thermistor lor. Okay, thermistor, hopefully you've seen it before. So down here is the picture of the LDR. You see the snaky pattern like that one? That is you can say that's where the magic happens. I think it's a cadmium sulfide. Oh, is it sulfate? I think it's sulfide. You can go to Google search lah if I'm wrong. Cadmium sulfide strip, and when it's very bright, a lot of stuff will happen here that will cause this thing to change its resistance. So let's take a look at what are thermistors, LDRs again, and how we can use them in circuits to make sensors. Last time we looked at the little black thing over there, that's a thermistor. We look at the graph, the curve, what kind of circuit. This time we're just going to focus more on how it changes with certain physical properties such as temperature, light, and things like that. So remember I said a long time ago, the resistor marry a semiconductor, love semiconductor, and they had a child called the thermistor, right? That is kind of like a resistor but with semiconductor properties. Actually, there's another child, two children. The first children is the thermistor. The second child, often forgotten, is the LDR. Also kind of like a resistor but with some semiconductor properties inside of it. So the LDR is on the right side lah. This is our LDR. Okay, refresher on what a thermistor is. The symbol looks something like this. Okay, like a resistor, but with the extra line like that through it to show that, okay, kind of like something changing. And what happens in this thermistor is when you use it in circuits for applications, like what we're going to do here, when it's hot, shall I use red color for hot? When it's hot, how does the resistance change? When it's cold, how is the resistance different? So when it's hot and cold, there is a certain graph for it. We have looked at the graph. It looks something like this. It's from one of those past years. If you have resistance against temperature, it's gonna look like that. Don't touch the curves. Don't touch the sides. Okay, if your temperature go very hot, eventually the thing will melt lah. So there's a certain limit of temperature it can go until. So up here is where we call the hot region. Down here is temperature very low, so colder lah. So when it's hot, the resistance is very low, you see? So low only leh. So when it's hot, R is low, or R reduces. Then when it gets colder and colder, R gets higher. Resistance high. And you can use that as a sensor for temperature, like we talked about the fridge. Okay, so when it's hotter, less resistance. That's this part. Now what about the LDR? The LDR also very similar. You draw it like a resistor. What's the symbol lah? Or maybe you remember the circuit symbol page that I sent to you, or you found in syllables. The LDR is a resistor but with light coming in. So you will see two arrows point into the resistor, which is the LDR, the symbol for the LDR. Now I said light, right? So it depends on light. That's why it's called light dependent. So how do you draw this out? Well, if you have resistance, what am I going to put on the x-axis? Light? Yeah, we could do that. Let's put light intensity. There's a certain unit for it, but we don't need to worry about that now. Basically, it means brightness lah. How bright is it? And also, it will also have the same kind of shape like that. Why leh? Because when it is bright, what shall I use for bright? Do I have an orange pen maybe? Ah, yes, I like this. So when it's very bright, light come in. Wow, then got a lot of free electron will come out there. So when there's a lot of free electrons, that means your resistivity will decrease or be lower lah. Decrease or is low. So that's talking about this part when it's very bright. Lots of light shining, lots of electrons, and free electrons inside can freely move around and help make it more conductive. Conductivity increase lah. So resistance decrease. What if it's very dark? No light. That's on this end. Okay, so maybe like somewhere here lor, for example. Wow, resistance very high oh. Just now when it's bright, resistance is very, very low. So when it is dark, you can guess the opposite happens. There's very few free electrons inside the LDR to conduct electricity. So here you can say like the resistance is very high. So increases as it gets darker or very high. So very useful if it's bright, suddenly got a lot of current can flow through this because resistance is very low. That's how we use it as a sensor. Okay, so think about that for a moment. If you need to sort out these two in your brain, don't confuse them. Okay, let me just draw dotted lines. If it's hot, resistance is low. If it is cold, for example, here, resistance is much higher. If you want to remember this, think of this. Cold resistance means it's high resistance when it's cold. It's a resistor when it's cold. The other one, you think of it as dark resistance. When it's dark, it's high resistance, like a normal resistor. When it's bright, resistance drop a lot. Okay, so we're going to look at just a few questions because there's not many of them. A few questions to help us think about LDRs and LDR with thermistor together and other kinds of circuits that may use both of these in the same application scenario. 1. This first one is on page 10, a pass here with a very simple light LDR circuit. So here we have a light LDR resistance of 1 ohm in the dark. Oh, okay. Oops, wrong pen. Sorry about that. Or 1 ohm in the dark and 1 kilo ohm when illuminated. Illuminated means got light lor. So 1 kilo ohm when bright, 1 mega ohm when dark. It is connected in series with a 5 kilo ohm resistor. You may be wondering why they put this one here leh. Or just in case you don't want to short circuit. You don't want current to be too big, so you put other resistors lor. And 1.5 volt, negligible internal resistance. Good. Makes life easier. So here's our circuit. We have this LDR which goes from, what's the range of it? 1 kilo ohm until 1 mega ohm. Now this LDR, light dependent resistor, is illuminated in a dark room by a flashing light. So in the dark room, you just on the light. Flash, 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 flash at it. And they'll ask us, which graph best shows the variation with time t of potential difference across R? What? Oh yes, we are trying to find what if you connect a voltmeter to measure the potential difference across, well, connect to the wire lah, across this R. So you're finding V here. How will the graph look like? Okay, let's look at the choices we have to get an idea. The only annoying thing is it's on the other page, so I have to scroll up and down, up and down. Okay, so take a look at this one. Try to make a guess which one you think will be the graph for this. When you shine, something happen on the LDR. When it's dark, something happen on the LDR. When it's bright, dark, bright, dark, bright, dark. That's why you see the up and down now. But which one is it leh? Try pause the video, take a choice, and make a guess which one you think is true. Also, by the way, I forgot to mention, on this page, this one is a typo. This should be ON12 P13. So other questions on this right side of the page is different lah. So when you find answer, make sure you know it's different. Okay, so let's Let's go back to the circuit. Okay, just try to remember how the graphs look like. If you can find a past here on the browser, good lah, then you can see also. Okay, let's see. How will the graph look like? Let's try to draw it out here on this page because we can see the thing here. Okay, so we have a couple of choices now. V against T, 1.5. Okay, now you need to think of how this one, LDR, is sharing your potential difference with the other 5 kilo ohm resistor. Because this V plus this V must be the same, must be equal to 12 volt, 1.5 volts ma. Okay, V plus V must equal to 1.5. So, when the LDR is 1 kilo ohm, when is that? 1 kilo ohm is in bright. Okay, so you say this is when it's bright. 1 mega ohm is in the dark. So maybe you start off with the dark law, you haven't flashed the light yet, so your graph will start off at the dark. But why is it 1.5? Because when you draw it like this, 1.5, 5 kilo ohm, and 1 mega ohm. Wow. That means almost all the potential drop will be across this 1 mega ohm. Because its ratio is so big. This V is big. Means almost 1.5. How I know that leh? You can calculate, man. You take the ratio of this one, 1 mega over the total. So 1 mega plus 5 kilo. That's the ratio of this fella across the whole total resistance. Equal to this fella's potential difference across the whole thing, which is 1.5. You calculate and see. It'll be quite big, almost 1.5. So that's going to start off at 1.5 up here. Actually, let's use purple. Then once you shine the light, what's going to happen? When you shine the light, it's going to change. So let me draw down here. I need more space. 1.5, the same thing. 5 kilo ohm. And now very small, 1 kilo ohm. Okay. So now it's going to drop to be much smaller, much smaller. If you want to calculate, sure, we can do a calculation so you can see what I mean. So if you know here is going to drop, but how much you see the answer? It will drop to a certain height, or it could be either A or B. Let's calculate and see. So 1 kilo ohm over the total resistance will be 5 plus 1. This is the resistance over the total resistance equals to the potential drop across it over 1.5. So what is this number? Check and see. This is a reality check to see if it goes to 0 or not. I don't think so. But we want to see the numbers. So 1 times 1.5. 0.25 volts. That's not exactly small, not like 0.000. So, it's going to drop down to 0.25, which is roughly here, half. So you're going to see a graph that looks like this. Dark, bright. Then dark, bright. Dark, bright. So that's where, oh my word, that's a not straight line. So dark, bright, something like that. So on, off, law, you can activate a circuit based on light. So with this graph in mind, let's go and see our choices. Here. Okay, so this one's not quite right because it's supposed to go much higher. This one, two problems with it. It never goes up to 1.5 and it's kind of at 0. So no, it doesn't really touch 0. That leaves us with A and B. To scale, roughly, this is 0.75. So B is probably more correct because you want to go down to 0.25. I think that's what we calculated. So B is the answer for this case. The potential difference across the LDR will just go up and down, depending on whether you shine a light or not. Now, here's another question that we're going to look at that has a thermistor now. LDR and thermistor working together. This neat question on page 21 is Yes, the two children working together, LDR and thermistor. Ooh, I like. So the diagram shows LDR and thermistor forming a potential divider. Yeah, because the potential is shared out between both of them. That's what we call a potential divider. We'll see more of this in chapter 20. Okay, here it is. Under which set of conditions will the potential difference across the thermistor, which one is the thermistor? Can recognize? Must remember the symbols, okay, the circuit symbols. You must know which is which. Thermistor, so this one, you're trying to measure what's the potential difference across it, have the greatest value. When will this have the greatest value? Hint, hint. If you try to think of the current things, there's going to be a lot of changing currents. So it might be easier to think of voltage and resistance ratios. That's my hint. So now I want you to try, take a guess, look at your notes or stuff that we have discussed earlier. You can rewind the video and try to see what should be the conditions of these two. Illumination means brightness. How bright is it? Bright, dark. Okay, pause the video, take some time, and must do it. Try out. Okay, let's see. So potential difference, we're looking at potential difference. Potential difference, if say, for example, if this is 9 volts, then your 9 volts will be divided across these two. If this one is 3 volts, this one is 6 volts. If this one is, what else can we have? 4.5 volts, this one is 4.5 volts. Maximum only 9 volts, so they have to share out according to their resistance. So, the LDR, this one, LDR, will have some potential difference, but we want to look for the purple one. When is the purple one the greatest? This is where we have to crack our heads to think a bit. So you want to say that because this one have bigger potential means this one must be much bigger than the orange one. So greatest value, that occurs when the resistance, let's use R. R of thermistor, okay, is much larger than the, or not much larger, just larger than the, what's the other one? The resistance of your LDR. This is the first important hint. Your R of thermistor must be much bigger compared to your R of LDR. So that means you have to think of, when is your thermistor resistance very big? Think of it. So you think, remember, high R means cold. Very cold, then the resistance of this one will be very high. Then the LDR, when is the resistance very small? Okay, because this one have to be small r, or smaller lah, small r. This one have to be a big R. When is LDR very small? Then you have to think of light, lor. So small r occurs when it's very bright, or your illumination or light intensity is very high. So based on these ideas, now you go and see. Thermistor have to be cold, so temperature have to be low. So these two out already. Yes. This one wrong. LDR have to be bright. That means illumination must be high. So that leaves us with B. Not low, not low. And B is how you can decide this one. Okay, if you kind of find like, Miss, I'm kind of mind blown at the moment. It's okay. Take your time to go through this. Rewatch this segment 10 times if you need to. Ask a friend, post some questions in the questions channel. Now we're going to go to a paper 2 question, which we started last time but didn't quite finish because there was an LDR in there. Okay, page 56. So on page 56, yep. Okay, so I want you to try this out first. The first part especially, should be able to try out some stuff. Take a maximum of like 10 minutes to try to get through to the end. If you didn't reach the end, that's okay, especially part B. Part C. Part C is where the LDR comes to play. But try out part A and B at first. Okay, so at least you can mark that out. Yeah, you will need 10 minutes to do that. Okay, first things first, potential difference. We have done this a few times, so hopefully you can remember how to do that now. Definition is work done over Q, or energy changes over Q. So you can say potential difference is the work done, or you can say energy transferred because E over Q. Oh, I say work done per unit charge. That is how we define potential difference. How much work is done to move a charge from here to here across a potential drop. Okay, that's on just a B1 mark now. Okay, definition, start off with that. Then you come to a circuit. This question is all about changing resistance, varying resistance. You start off with a variable resistor or rheostat. Battery, 0 internal resistance, good. Connected in series, 2 resistors. Oh, this one got arrow. Got arrow means the resistance can change on. Not because of light or temperature lah. It's just you can change it now, you turn the knob. Resistance of R2 600, R1 can change. Calculate the maximum PD across R2. Now, please say you have tried this already. But when is the maximum PD occur? It's basically saying if I connect a voltmeter here to measure the potential difference, when is that value the biggest? We talked about it just now. If you have 2 resistors, you share out the potential of 20 volts. But if this one is 0 ohms, then the whole thing can be here, 20 volts. So do you need a show working for this? Well, not exactly. I mean, sure, you can show working, but let me check the mark scheme if they'll give you extra marks for that. And nope, no extra marks. So you can just straight away say, you see, it's 1 mark, right? So don't overthink this. If you see a 1 mark question, it's like, oh, it's probably just, 20 volts. Yep, that's true. When this R1 is 0, you get 20 volts over here because it's basically like this, ma. It's like this. 0 ohms means it's basically non-existent. So all you have is here, 600 ohm. And if your battery supply is 20 volts, means you have a 20 volt drop all across that one resistor. So just write 20. That one straight away will give you a A1 mark here. Yeah, so if you overthink it a bit, just make a note like, hey, don't overthink. It's actually just like that. Then part 2, minimum PD across R2. When is it minimum? Oh, let's draw out some pictures now. When it's minimum, that means the other resistor has taken quite a big share of it. So that will probably be 400 ohm. And here will be same 600 ohm. And 20 volts. Is it 20 volts? Yes. How are we going to measure that thing? You could use currents to calculate it, like find the current and then use current to find. But I'm going to shortcut and use the ratio method. Because then I don't need to worry about current. Yeah, you can find current and then you find the V. But here we go. Ratio method, if I want to find the potential drop across this one, what I need to do is I take that fella's resistance over the total resistance, which is 400 plus 600, equals to the ratio of that fella's V, I use purple lah, then you can see per V, over the total potential drop across all the resistors, which is 12. Then what do we get? V equals to 600 over 1000 times 12. 7.2 volts. Correct or not? Check and see. I found the error. Sorry, not 12 volts. I was looking at another circuit on my paper. 20 volts. That's right. If you saw the error, good job. If you didn't, maybe your brain is lagging a bit lah. Okay, never mind. So now 20 volts. 12 volts. So that means you have a 12 volt drop right here. 12. Okay. Then, this one is 2 marks. So 1 comes from you using whatever method. You can find the current and then use current to find V. Can C1 and then A1. Okay. I'll just write out here lah, the current method, which can be quite complicated if your circuit is very complicated. I just write the steps. First, use total resistance to find the current. I. And then after that, you use VIR to find V for R2. Okay, because the current will flow through like that. You know current, you know ohm, you can find V. Both method work. Make sure you know how to use both. Now we come to the part where it becomes exciting because you're like, wow, what is this? You see now they add the LDR connected in parallel. This one is a new one. Before that, this thing was not here. New. And what do they ask us to do? Let's go up. When the light intensity is varied, the LDR resistance changes. For the maximum intensity, calculate total resistance of R and LDR. Maximum light intensity, which one is that? Is it 5 kilo ohm or is it 1.2 kilo ohm? Think about that. Maximum light intensity means it's very bright. Very bright means your R is your lowest. Maximum anymore. So R lowest you see 1.2 kilo ohm more. So this is the one. So if I redraw the circuit here, it's going to look like this. 20 volts, the variable resistor, and the LDR, yes, which is now at 1.2 kilo ohm. And then of course the other resistor down there. Connect and go back. Okay, so they're asking us calculate the total resistance of R2 and LDR. So they're looking for the resistance of this parallel section here. Okay, what's the total resistance of the what's they call it? What is this colorful? Parallel resistance. So you need to remember, how can you combine parallel resistance? Well, 1 over R of that parallel resistance, I put here P parallel resistance, equals to 1 over the LDR, which is 1.2 kilo ohm, plus, what's the one down there? Check and see, 600 ohm. So 1 over 600. But also, you need to, this is 1 over RP, so you need to change it to become 1 over this whole thing, this whole bracket on the right side, or you just put negative 1. It's the same thing. So 1.2 times 10 to the 3, 600. Now, press your calculator to see what you get. I pressed already. This one I calculate already. 400 ohm. So you write 400 here. 2 marks. 1 comes from your final answer. 1 comes from you knowing how to combine resistors in parallel. So C1. This thing, the 1 over R equals to 1 over R1 plus 1 over R2 formula. Chapter 20 will see where this formula comes from. Okay, not too bad so far. But now, they ask us to explain. At the end of each question, sure got explain one. Or draw graph. The resistance of R1, which is R1, this one, is varied from 0 to 400 in the circuits figure 6.1 and 6.2. State and explain, double action word, the difference between the minimum PD across R2. Minimum PD across R2. What are we trying to measure? Okay, so much more drawing now. I'm going to draw here. So that is figure 6.2 and can be simplified to become like this. One resistor, second effective resistor, because you already combined the parallel resistance, and just now you found is 400 ohm. It's 6.2. And this one you can change from 0 to 400 ohm. Okay, 6.1, you kind of have to scroll back to the previous one. Oh yes, that's the original one. 6.1 is the old one before we add the LDR. That's just the variable resistor and a normal generic resistor of 600 ohm. So they're asking us what's the minimum PD across R2. In other words, here, if you measure that, V will have a minimum because of this 0 to 400. Here we'll also have a minimum if you measure the V across the 600, which is R2. Here R2 is inside there, but it's parallel, so it's the same thing. R2 plus LDR. Okay, so how are we going to describe this thing? Minimum PD occurs when, what is that? When this other resistor has taken a big share of it. What do I mean by that? I mean, when this thing is the maximum, 400, then this purple V here is the minimum. That's what we're talking about. So in both cases, minimum 400. But how will the minimum change? How is this V from the 6.2 and 6.1 going to change? Here's how you can describe it. First point, the total, well, you say total parallel resistance. Parallel resistance means the LDR plus R2 add together, or the rainbow thing that I draw on top there. The total parallel resistance in 6.2 is 400 here, 600. So how to change? So you want to say the total parallel resistance in 6.2 is smaller than R2 alone in 6.1. Take some time to think about that statement first. So the next statement, you can say, so the minimum PD is reduced. Well, minimum PD across R2. You can put the whole sentence up. I'm going to say minimum PD is reduced when LDR is added. Now, it might seem kind of abstract. You're like, Miss, how you come up with this conclusion? Well, if you're not convinced, you calculate. In the original one, part B, we already calculate the minimum PD is 12 volts here. Right? But if now we have added the LDR, you have an effective resistance, parallel resistance of 400. 400 and 400. That means your voltage drop across the LDR plus R2 here is half. So 10 volts here. And then this side will also have 10 volts. They share ma. They have same resistance, so they share the equal potential difference. So minimum potential difference drop already. This is the minimum PD, 12, drop down to 10 when you add the LDR. So that's how you can talk about it. You need to state and explain. The state one is this one. Explain is you have to talk about resistance. Where do the marks come from? 2 marks for this one. Let's check and see. It's a M1A1. So here you must talk about resistance M1 in order to get your A1 mark. If you just say minimum PD is reduced, then you don't get your mark only. You must explain. Oh, this one very strict. M1A1. Okay. So that's all for this question and the LDR series. Go and try out some of the few questions. There's only a few of them down in the description below. Go try out some of these LDR questions, Thermistor questions, and see how they are used in different applications. That's all for this video. Now it's really the end of chapter 19. No more bonus videos. At least for now. I'll see you in chapter 20, coming up next.